In this video, we're going to look at AP Practice Problem 7 and what are the answers and how do you get all the points? What are they looking for? All right, in this problem, they're talking about the ability to visually search. They want to see if video games can improve this ability amongst people. They tried 3 different video games. There's a driving game, a sports game, and a puzzle game. And they basically picked 60 volunteers who have no experience playing video games and want to see if the games improve their ability, and if so, which game does it the best or whatever. All right, so everything in this problem is based on that scenario. So let's move to problem A. It says describe an appropriate method for randomly assigning 60 participants to 3 groups so that each group has 20 participants. Now, when you describe this, you need to pretend that you're actually describing this to someone to do, like sort of a step-by-step process. Because basically, if you just go, oh, well, randomly pick some people, it's not good enough. Pretend that you're actually trying to communicate to someone how you would do this, right? So there are lots of different answers that can work. I sort of outlined 2 that I thought of. Most people go nowadays for the computer program, but remember that you don't have to use a computer program to do this. You could use physical means. So one of my answers talks about the computer program. So I'll talk about that first, and I'll talk about a physical way you could do it, which probably would be maybe even a little better. Because a computer program, you got to get to do what you want. So you could assign each person number 1 through 60, and then use a random number generator to randomly pull these number outs. But the key thing is you need to realize that there need to be no repeats. If you're just using a random number generator like we did in class, well, you might generate 3, and then you might generate 3 again. And what are you going to do? You're going to keep generating. Now, you could just ignore that 3 and keep generating, but you could be there for thousands of pulls trying to get 60 unique ones. So you don't want that to be the case. You want a random number generator that doesn't allow repeats. That way, once you pull out 3, 3's out of the pool, and it'll randomly pick from what's left. You do need to mention after you go, well, how are you going to pick them? How you're going to assign them. So you're going to assign the first 20 to group 1, the next 20 to group 2, and the third 20 to group 3. But you have to describe what the groups are. So if someone were actually doing this, they'd be like, well, what's group 1? So on the side, I made sure I define that. Group 1's the driving group, group 2's the sports group, group 3's the puzzle group. You have to be very specific. So if someone were doing this, you'd go, well, use the random number generator this way, make 3 groups of 20, and then make these the groups. I want group 1 to be the driving people, whatever. When people describe this, they often forget this part, right? They don't define the groups. But you would want to do that. You would want to know group 1 is the driving group, for example. It's meaningless if you don't know that, and especially if the person who's working this might go, well, I don't know who you want where. I don't know what group. I know I made group 1, but I don't know what I'm supposed to do with them. So think about a person actually doing it. Now, I also added in, because it's so tempting to use a computer for everything. But, what would people have done, 50 years ago before there were computers in everyone's pockets? I mean, there were computers 50 years ago, but they were, the size of buildings and stuff. So, and you go back 200 years, and now you don't have any kind of electronic computers whatsoever. So what could someone do without computers? You could also put everyone's name on a slip of paper, put them in a bucket, shake it around, sort of like what I did with the numbers in the box when we were doing looking at sampling distributions. You could shake it constantly, randomize them out, and just draw them without looking. And same thing, then you'd want to go, well, the first 20 I pick out are going to be the driving group, and the next 20 I pick out are going to be the sports group, and so on. All right, so these are 2 different ways. They're not the only ways, but when I go over how it was graded, you'll be able to see, what were they looking for. The key thing in here is some kind of random assignment, and then describing how you're assigning people and what the groups they're going into. All right, so it's specific. The next part is they want to see if there's a significant difference between 2 of the games. So they want to see if playing the driving game would lead to a different mean improvement time than playing the sports game. So essentially, is the driving game causing more improvement? Is the sports game causing more improvement, or is there are they the same? Maybe there's no improvement at all, or maybe they have the same level of improvement. So we're comparing them amongst each other. So they go, assuming the appropriate population values are approximately normally distributed, state the name. So they're basically saying, assume that this is going to be a good thing, that it'll work. What test would we use, and what would the hypotheses of that test be? So this is being, we're looking at the averages from two samples. So if we're looking at averages, we're not doing a two-proportion test because we're looking at means, so we're doing a two-sample t-test. So realize, since we wouldn't normally have the they don't say anything about population standard deviation, so we're doing a t-test, not z. So this is a two-sample t-test for the mean. So we want to see if there's a significant difference between the two samples. Remember, a two-sample t-test, our assumption is there is no difference between them, and the alternative would be there is a difference. So when I showed this in class, we put that if we subtract the two means, it's nothing. That's our null. Our null is assuming these two populations are the same. And then the alternative is going to say, well, when I subtract the two populations, forgot my one there, when I subtract the two populations, there is some difference. Now, this can also be written as mu1 equals mu2 and mu1's not equal to mu2. So there's different ways of writing them. But the other key thing I need, besides the two hypotheses and the name of the test, is you have to define what each one of these things are. So one of them is the population number or population average for the search time improvement of people who play the driving game. And this is the population average search time improvement of people who play the sports game. So you have to tell somebody what these things are. Because when I go, oh, mu1's equal to mu2, or mu1 minus mu2 equals 0, someone needs to know what the heck the mu1 and mu2 are. Now, in the problem, they're talking about the sports games, but you need to define them, especially if I was subtracting these and they wanted a one-sided test. Would I make this greater than or less than? Depends on what I called these. So this is a classic thing people forget as well, as they forget to define these, because basically we're used to just going, okay, let's just put these symbols down, but make sure you define what the symbols are. So here, once I define these as the average search time of the population for these different games, my null assumption is that they're going to be the same, and then my alternative is if I have evidence against them being the same, I'll think that they're different. Part C asks about if the appropriate test was performed and no significant difference was found, what's something that could increase the power of the test? So power is your ability to reject the null if it's wrong. So the assumption that comes with power is that the null hypothesis is a mistake. So if you're going to test the power, this would be false. They wouldn't be the same time. One game would be better than the other. The problem is if one game's only better by like 2 seconds, it's hard to prove that it's the game itself and not just natural variation in the samples. So power is our ability to see that if there is a difference, can we attribute it to a difference in the population and not just natural variation of the samples that we took. So the best way to increase power, the easiest way to make this work, is to increase the sample size. What would make it easier to prove the null was wrong? Well, it would be to grab so many people that there would be very little dispute. So, for example, if I just grab 2 people, I have one play one game and one play the other, and there's a 2-minute difference, and I go, oh, look, well, the driving game's better because, look, this person was 2 minutes better than the other person, you should question that, because you'd go, well, the other person could just be better at video games, right? If the other person's just plain out better, it may just be luck that I got, one person who varied a lot, and it was hard to tell the difference from the game, from the game's difference from the individual's difference. Now, if I came to you and said, well, I had 5,000 people play the driving game and 5,000 people play the sports game, and the 5,000 who did the driving game did better on average, did 2 minutes better on average. That would be a lot harder to fight with. Because you go, well, out of 5,000 people, all of these people are doing better, or on average, as in aggregate, they do better by 2 minutes. That's way more convincing that it works on everybody in the population, because those, 1,000, 10,000, however many people you grab, they're not the entire population. But when you grab so many of them, it's hard to grab so many people and have them not be representative of the population. So the best way is to increase the sample size. Now the reasoning is, here's the technical part. You want to increase the sample size because increasing the sample size makes the standard deviation or standard error smaller. In the formula, it's S over square root of n. So when you divide by a bigger number, your standard deviation goes down. What this does is, if you detect a difference, if your samples are different, remember what allows you to know if they're significantly different is how many standard deviations apart they are. If you make the standard deviation very small, so say they're only apart by 1 minute, but the standard deviation is 1 second, well then they're 60 seconds apart, and that's 60 standard deviations. So increasing the sample size shrinks the standard deviation, thus making detecting an actual difference easier. So if there is an actual difference, we'll have a better way of detecting it. If the standard deviation is larger, well, then it, like say they're 1 minute apart and the standard deviation is 50 seconds, well, they're a little more than one standard deviation away from each other, and that could just be from natural variation, all right? So this is the logic that if you really, really want to shore up this question, you would say, well, the sample size increases, it makes the standard deviation smaller, and this allows us to detect an actual difference, since a smaller standard deviation will make any difference have a higher t-score, which is like the z-score. So basically, this is number of standard deviations. We'll have a higher t-score and possibly make it a significant difference, okay? So it's not guaranteed to do that, but the smaller standard deviation, it doesn't matter how far apart they are. Really, really tiny standard deviation is way more likely to show that difference, all right? There is one other answer, has to do with increasing the alpha level, and this comes up in another problem. You could also increase the alpha level. That's your cutoff. So the cutoff is normally 5% when you do a test. You could change that level, because basically the alpha level or the cutoff is your chance of making a type 1 error. So if I set the alpha level 5%, I have a 5% chance of making a type 1 error. Now, what's this got to do with power? Well, power has to do, it's the opposite of type 2 errors. But if you increase the alpha level, what it does is it actually makes type 1 errors happen more, but it makes type 2 errors happen less. And if type 2 errors happen less, it means you're doing the right, you're rejecting correctly, and that means your test is more powerful. So another thing you could do, the second answer to this would be, if you make the alpha level higher, you're going to be basically, put the cutoff at 10% or 20% or something ridiculous. That means you're going to be rejecting the null a lot. Now, if the null is wrong, that's good. You're going to up the level at which you reject the null, and that's going to make you reject more often. It's sort of a cheap way of doing it, because like I said, if you don't know the result, basically this is going to make type 1 errors happen more. But since we know that there is an actual difference, the test would be better if the alpha level were increased. All right, so the second answer, and like I said, it doesn't matter which one you pick. This is probably the best answer, but this one's also acceptable. If you increase the alpha level, it will make a type error happen more often, but this will result in making type 2 errors happen less often. Since type 2 errors will happen less often, we'll mistakenly not reject the null less often, meaning we won't make that mistake and we'll have a more powerful test. It will reject a wrong null hypothesis. All right, so that's the technical stuff. Get that wire out of the way. Let's look at how they graded it. So part A, in order to get all the credit in part A, so this was talking about how to assign the people. They were looking for these 4 things. Your method needs to be random. It needs to guarantee equal probability of assignment. Usually if you pick something random, this will happen. I mean, not always, but most methods you pick, like shaking a hat or a computer generator, this would be covered under random. You need to also have your method result in 20 members per group. You have to say that explicitly. So you have to make sure you say, well, I'm going to do this 20 times and throw them all into group 1. And then the last part says you need to specify which game is assigned to which group. So you say throw 20 people in the group 1, you need to know group 1 is the driving group, all right? So basically, I feel like there's really 3 parts here because most of the time, these 2 things, I said, most random things people would pick would also cover this. So basically, you need it to be random. You need 20 people. You mentioned that how you're going to get 20 people in the group and what group is which. If you did that, you get an E. 2 or 3 out of the 4 get you P, and then an I otherwise. Part B, that was making those null hypotheses and naming the test. Well, you get a point for naming the correct test, a 2-sample t-test for the mean. 2 for defining the parameters, this is what most people miss, and then 3 for writing the null and the alternative hypothesis. So I showed that, like I said, my answer includes those things. So E is if you do all 3, P is if you do 2 out of 3. And if you don't do 2 out of 3, well, then you get an I. And part C has 2 things that they're looking for, that you put one of those 2 reasons down, that either you know the sample size needs to increase or the alpha level needs to increase, either way, and then provide the reason behind it. So the problem with the 1 and 2 here is the E is obviously both. For P, you need the first and some kind of, or an understanding of what power is. So you need the first with a weak backup. So you need some kind of reason. You can't just say increase the sample size and get credit. You need that with some kind of extra understanding of what's going on. All right. Basically, those are the 3 parts. You get an E, a P, or an I for them, and then here's the scaling out. They're basically always the same for these 3-part questions. 3 E's is a 4, EEP is a 3, and then these like sort of double hits, EEI, EPP, PPP, or EPI. These are all 2 points. 1 essentially correct or just 2 partially correct gets you down to 1 point. Anything less than this is a 0. So if you have like 1 partially correct, it's not good enough. All right. So that ends this video. That was AP Practice Problem 7. Sorry, it has a bunch of technical stuff about tests in it, concepts that are good to know. All right, see you in the next video.